set the stage, what counts as an interstellar object, why they matter, and the lineup Oumuamua 2017 and 3IATLAS 2025 define hyperbolic interloper in plain English and explain why these are planetary system crumbs flung into the galactic hallway. Quick laugh. Interstellar objects are cosmic couch surfers, no forwarding address, unlimited wanderlust. Before these three showed up, most space rocks we studied were local-born, baked and battered within our own solar family. An interstellar object breaks that mold. It is a visitor with paperwork stamped elsewhere, carrying a trajectory that refuses to loop back to the sun. The simplest test is geometry. Plot its path, and if the curve is open, not closed, you have a runner. In celestial terms, that open curve is hyperbolic. In human terms, it is the difference between a commuter and a tourist who keeps the engine running. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes it's best enjoyed the way you'd enjoy a late-night conversation, quietly with a cup of tea and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure. Only if you enjoy these calm journeys through the universe. Now let's begin. Hyperbolic interloper sounds like somebody exaggerating at a party, but it is actually a precise label. Hyperbolic means the orbit's eccentricity is greater than 1, so the path is not an ellipse that returns, but a swoop that slices in and sails out. Interloper just admits the object is not from here. It cuts through our neighborhood like a shortcut through someone else's backyard. If ellipses are the universe's polite circles, hyperbolas are the drive-by wave. The sun's gravity bends them, sure, but cannot leash them. Think of the sun as a celebrity barista. It can influence your route past the cafe, but it cannot make you sit down unless you already plan to. Why should we care about these passers-by who never stay for tea? Because they are samples from other planetary kitchens. Comets and asteroids preserve the original ingredients of their home systems, the ices, dust, and minerals that never got cooked into planets. Catching one mid-flyby is like finding a breadcrumb at the edge of a banquet and still inferring the chef's entire menu. If we want to know how typical our solar system is, or how wild the exoplanetary suburbs get, these objects are the first physical hints we have that are not filtered through starlight and clever math. In short, telescopes find the exoplanets. Interstellar rocks bring the gossip. Our cast? First came Oumuamua in 2017, a dim sliver that zipped through on a trajectory signaling not from here. 2 years later, 3I Borisov arrived, the second interstellar visitor and the first that looked comfortably comet-like. Then 3IATLAS followed in 2025, a newcomer with its own personality, reminding us that space has genres, not stereotypes. We will meet each in depth later, but for now they function as archetypes: the enigmatic drifter, the textbook comet from out of town, and the fresh arrival who refuses to fit neatly into either box. If this were a heist movie, we have the wild card, the professional, and the new recruit, all with different skills, all with passports stamped galaxy. How do such objects exist in the first place? Picture a young planetary system, a swirling disk of gas and dust, where planets grow from collisions that range from polite bumps to demolition derbies. Giant planets, when they form, become gravitational bounces. They can toss smaller bodies inward to be vaporized, outward to become distant residents, or, if the timing is right, fling them so fast they break free of their star entirely. That final fate is escape velocity squared, a slingshot event that launches a pebble into interstellar anonymity. Over billions of years, the galaxy accumulates these castaways like a cosmic lost and found bin, with no attendant and even less labeling. By the time one of these drifters reaches us, its exterior has been sandblasted by radiation, micrometeoroids, and temperature swings that would make a thermostat weep. The surface might be crusted, darkened, or dehydrated, while the interior keeps secrets like a locked diary. The sun's heat can wake up buried ices, but from a distance we only glimpse what leaks or reflects. A frustrating game of what's in the box, where the box is tumbling, the light is terrible, and the clock is ticking. Observers chase these targets in brief windows of visibility, gathering photons like hurried reporters shouting questions as the limousine pulls away. Calling them planetary system crumbs is not an insult. Crumbs are data. Each crumb retains the recipe of its birth environment, the balance of water, carbon monoxide, carbon dioxide, silicates, and exotic organics, the sizes of its dust grains, the scars of its collisions. Even their shapes and spins are forensic clues. Is the object rigid or a rubble pile? Does it tumble chaotically or spin neatly? Answers to those questions hint at whether it formed gently in the cold outskirts or survived roughhousing near newborn giants. The stranger the behavior, the more precise the story it can tell, like a plot twist that suddenly explains the earlier scenes. There is also a philosophical delight here. For centuries, we looked outward at other stars and imagined their worlds. Interstellar objects invert the arrangement. The worlds send pieces to us. No need to resolve a tiny exoplanet next to a blinding host star. The courier has arrived, wearing a dark coat, refusing interviews, but leaving enough fingerprints for a lab report. That is why hyperbolic interlopers are more than orbital curiosities. They are messengers from systems we may never see directly, moving too quickly for capture, but not too quickly for comprehension. The universe, it turns out, does unsolicited mail, and occasionally it is not spam. So take a breath. The three visitors are not threats. They are opportunities with deadlines. They flash through our sky and through our questions, forcing us to sharpen techniques, build faster coordination, and invent better stories that match the evidence. The Milky Way is not a closed book exam. It is an open note course where the notes drift by at several dozen kilometers per second. Next up, we will rewind to the moment of discovery and show how these travelers were actually spotted, because the universe does not announce arrivals, and our telescopes had to learn to catch the door swinging. Sky surveys are basically cosmic motion detectors, except the cat is traveling 60 kilometers per second. Oumuamua did not kick open the door so much as trigger a careful researcher's instincts. On October 19, 2017, Robert Werrick, working with the Pan-STARRS 1 telescope atop Haleakala, noticed a faint speck sliding between frames, with the kind of speed that says, "I don't live here." He linked fresh images to earlier ones, ran the object through the pipeline again, and the track still refused to curve like a normal bound visitor. Pan-STARRS was built for this sort of what moved question. A 1.8-meter telescope with a gigapixel camera sweeping huge swaths of sky to catch anything new, variable, or suspiciously fast. It is the astronomical equivalent of a neighborhood watch, with excellent eyesight and a very patient memory. Oumuamua's discovery report went out, follow-ups piled in, and the story of our first confirmed interstellar visitor began with a handful of pixels and a hunch sharpened by good software. Pan-STARRS' strategy is deliberate. Cover a lot of sky, deeply enough that faint things still register, then come back on a rhythm that lets you tell motion from noise. Long exposures and a big field mean you can push to fainter magnitudes. A robust database means you can subtract yesterday's sky from tonight's and keep only the mischief. The cadence is not every 10 minutes everywhere. That is impossible, but it is often enough that fast drifters paint a telltale streak from night to night. The price of depth is that you cannot scan the entire dome repeatedly each hour, so you lean on a network of follow-up telescopes and rapid alerts once something interesting pops. Pan-STARRS is the marathoner, steady, wide field, and relentless, building context that turns one odd detection into a confirmed outsider. 2 years later, the interstellar headline broke not from a national facility, but from a backyard-scale obsession. On August 30, 2019, local Comet Borisov, an amateur astronomer and telescope maker, spotted a fuzzy point at his private Margot observatory. The instrument, a 0.65-meter telescope he designed and built himself, a tinkerer's answer to the universe's pop quiz. Early measurements hinted at a hyperbolic path. More observers swung to action, and within days the consensus formed: interstellar, and this time openly cometary. If Oumuamua felt like a spy thriller, minimal clues, maximum tension, Borisov was a documentary with clear footage. The human flavor here matters. Professional surveys cast the net, but passionate specialists, even working far from mountaintop behemoths, can still land the big fish. The global relay from one dome to another is the real star. Somebody finds, everybody checks, and the orbit decides. Enter 3IATLAS in July 2025. Caught first by the Atlas telescope in Chile, ATLAS plays a different game from pan-stars. Smaller apertures, yes, but an all-sky sprint repeated several times each night. Its job is to see anything new and moving quickly enough to matter for planetary defense, which also makes it great at catching strangers on fast inbound lanes. The Chile station at Rio Hurtado, observatory code W68, scanned, flagged a fast mover, and the software fired off the look again flare. Within a day, additional telescopes reported a faint coma. Not another stealth visitor, but an ice ball, and the Minor Planet Center stamped the third in history interstellar designation. The official NASA notes and news wires were almost giddy. Third time ever, and the first snagged by Atlas. Think of Atlas as the night shift security guard, walking the same loop again and again. If a new shadow appears, it notices before the coffee cools. These three discoveries show how complementary strategies win. Pan-STARRS' strength is depth with memory. It builds an enormous baseline of the usual, so the unusual cannot hide. It can also push fainter than many patrol systems, making it an excellent first catcher of dim, fast interlopers that do not light up like classic comets. Atlas, by contrast, is about cadence, scan, rescan, and rescan again, prioritizing speed and coverage over raw depth. The goal is to catch change in near real time, so that nothing barrels past unannounced. And then there is the wild card, the dedicated individual with a custom instrument like Borisov, who operates with flexibility and intuition, pouncing on low elongation opportunities and places the big facilities might temporarily overlook. In practice, all three approaches converge in a choreography. Survey pings, community confirms, specialists characterize. The near misses are as instructive as the hits. Oumuamua was first noticed after its closest pass to the sun. It was already heading out when the alarm rang. That is the tax you pay for a universe that refuses to schedule arrivals. Atlas's constant loops reduce that risk for some classes of objects, but no single system can watch everywhere, always at ultimate depth. The trick is coverage in layers, slow, deep maps, fast, shallow sweeps, and a responsive network that can sprint the moment a new dot jitters, where yesterday's sky was still. When the pipeline is humming, minutes matter. A fresh alert dictates where a dozen telescopes will point before dawn, like a newsroom shuffling assignments when a story breaks. There is also the culture that grew around these detections. Software carries much of the load: automatic difference imaging, machine learning vetting, trajectory fits. But the follow-through is human habit. Astronomers trading coordinates at ridiculous hours, observatories swapping time, amateurs waking neighbors, because trust me, you want to see this. That collaborative reflex is why a home-built scope can hand off to a space telescope in a single news cycle. When 3IATLAS hit the wire, professional and public eyes were already primed by two prior interstellar celebrities. And within days, the story moved from "we found a mover" to "we are mapping its path and watching its coma grow." The pipeline did not just work, it danced. If you are wondering how many we have missed, the honest answer is many. The sky is large, the objects are small, and the window is short, but the trend line points our way. Deeper detectors, faster cadence, smarter filters, and a community that treats each alert like a fire drill. In that sense, finding these interstellar visitors is not luck. It is preparation meeting opportunity at tens of kilometers per second. The cosmic doorbell has been installed. Now we are learning to answer it before the guest is halfway down the block. And that is how you spot the uninvited and keep them from becoming the ones that got away. Next up, we will follow the paths themselves, the geometry of not coming back, and explain how a simple number tells you when an object is only waving hello on its way to somewhere else. Their orbits scream, "I'm just passing through," louder than a tourist with 3 rolling suitcases. If you want to know whether a wanderer belongs to the sun or is only here for the snacks, you ask a single question. Is its path closed or open? A closed path, an ellipse, means gravity has the object on a leash. An open path, a hyperbola, means the leash snapped before it was ever clipped on. In orbital speak, the number that decides this is eccentricity. Anything less than 1 is an ellipse. Exactly 1 is a parabolic edge case. And anything greater than 1 is a hyperbola, the geometric handshake of escape. A hyperbolic orbit has positive energy and a speed it keeps forever, called the excess velocity, the speed it will settle to once the sun's pull fades to a whisper. That combination, eccentricity, above 1 plus a dungo excess speed, is the calling card of an interstellar origin. You do not get that kind of permanent exit ticket from casual dawdling around the planets. Oumuamua is the clean, almost textbook demonstration. By the time its track was nailed down in late 2017, the fit screamed eccentricity about 1.2, comfortably hyperbolic, far beyond what a gravity nudge from any known planet could concoct. Its path traced backward to roughly the constellation Lyra, only a few degrees from the solar apex, the direction our sun plows through the local stars. That is significant. If you scoop interstellar debris at random, more will ride in from near the apex, like bugs on a windshield. Oumuamua's inbound speed was already too high, long before it met the sun. And after the swing by, it was still in the no takebacks category. In human terms, it arrived with a carry-on already packed for departure. 3I Borisov, 2 years later, took the same cosmic exit, but with even more swagger. Its orbit is not just hyperbolic, it is extremely hyperbolic, with an eccentricity around 3.3. The geometry lesson hidden inside that number is delightful. The larger the eccentricity, the less the sun can bend the path. A parabolic borderline escape would reverse direction by roughly 180 degrees, a dramatic U-turn. Borisov, by contrast, was deflected by only a few dozen degrees, about 34, gliding through like a speed skater, taking a wide corner. Pair that with a hefty hyperbolic excess speed, and you have a trajectory that cannot be forged by a one-off planetary slingshot in our system. The sun played influencer, not keeper. Now rotate the camera toward 3IATLAS. Its approach direction is from the general area of Sagittarius, near the Milky Way's bulge, astronomically scenic, dynamically intriguing. That inbound geometry, coupled with a hyperbolic path, clinches its status as an interstellar passerby. NASA's orbital rundown highlights the same essentials. It is on a non-returning trajectory. It will skim the inner solar system, and then it will keep the promise printed in its orbit and leave. If you are keeping score, the which way did it come from answer is a different patch of sky than Oumuamua's Lyra or Borisov's high-latitude entry, which is exactly what you would expect if these are random castaways from many stellar neighborhoods, rather than a single conveyor belt of debris. Variety is the norm for a galaxy-sized sample. Hyperbolas also come with a useful gut check, the turning angle. Imagine the orbit as 2 straight lines that would continue forever if the sun were not there, the before and after directions. A barely hyperbolic visitor bends sharply. A wildly hyperbolic one barely flinches. Borisov's 30-something degrees fits that picture, while Oumuamua's more modest hyperbola allowed a stronger curve near the Sun. For 3IATLAS, preliminary fits place it squarely in the not coming back, not even tempted camp, with an eccentricity dramatically above 1. In tables of orbital oddities, it sits with numbers even larger than Borisov's, reinforcing the message that this is not a product of local gravity games. Think of it this way. The Sun tried to negotiate, the interstellar traveler kept walking. You can also hear the physics in a different key: energy bookkeeping. Bound orbits are like bank accounts with negative balances. You owe the Sun, a hyperbolic orbit is cash positive. The object arrives with surplus kinetic energy and can afford to tip the Sun's gravity on the way out. That surplus shows up as the excess speed, the asymptotic cruise control the object will settle into far beyond the planets. Oumuamua carried such a surplus. Borisov carried even more. 3IATLAS arrives wealthier still. If orbital mechanics had a customs desk, the declaration form would read: energy, positive, duration of stay, brief, purpose of visit, transit. Approach geometry adds flavor beyond the raw numbers. Borisov dove sunward on a path and tilt that made it behave like a classic comet, just one born elsewhere. So the solar heating turned its track into a luminous arrow through the inner system. Oumuamua's geometry was more of a drive-by: high speed, high tilt, brief solar handshake, then a swift exit that left observers scrambling to catch its light curve on the way out. 3IATLAS's approach from Sagittarius means observers in the southern hemisphere enjoyed the early vantage, but the dynamical lesson is the same anywhere on Earth. The sky location of the inbound leg is a compass pointing to the random, three-dimensional nature of interstellar delivery. There is no preferred lane on this highway, only probabilities set by how stars move and how their planets eject debris. All of this, the eccentricities, the turning angles, the excess speeds, the sky directions, builds a single verdict. These are not locals on elongated ovals. They are immigrants with one-way tickets. Planetary flybys inside our system can indeed pump energy, but not to the levels needed to mimic these tracks, and certainly not from multiple random sky directions that happen to align with broader galactic traffic. The orbits tell the origin story, even when the objects themselves are stingy with light. Gravity is not chatty, but it is honest. It writes confessions in conic sections. Next, we will trade geometry for personality, zooming in on how shape and spin whisper about internal strength. Because once you know how a traveler moves, the next question is what it is built to survive. If beauty is in the eye of the beholder, Oumuamua is in the eye of the baffled photometrist. Start with the only thing we truly measured in detail: how its brightness rose and fell as it rotated. That flicker, its light curve was dramatic, a swing of roughly 2.5 magnitudes. In plain terms, it brightened and dimmed by about a factor of 10, like a lighthouse trying out for community theater, for solid bodies reflecting sunlight. Such an amplitude usually screams extreme shape. Imagine a spindly baton. When you see it broadside, lots of surface catches the light. When you see it end on, it nearly disappears. That ratio between the wide and thin views tells you a lot about how stretched the object must be. A factor of 10 brightness swing pushes the implied axis ratio into eyebrow-raising territory. Think 6:1 or more, even allowing for surface reflectivity quirks. Cue the parade of metaphors. Early sketches cast Oumuamua as a cigarette, a distant cosmic breadstick, even a spear. Then came the rebuttal. Maybe it is not a cigar at all, but a flattened disc, a cosmic pancake tipped just so. Why would both shapes fit? Because our inference engine is working with silhouettes and shadows, not a resolved photograph. The light curve is a puzzle of geometry, surface scattering, and viewing angle. A thin, wide object can produce the same extremes as a very long, skinny one, if it is oriented correctly, and if its surface reflects light in a non-Lambertian way. Translation: the shine is not perfectly dull and uniform. We also viewed it at fairly high phase angles, the Sun-object-Earth geometry, that makes things look more dramatic, so modest physical differences can balloon into large brightness differences. In short, cigar and pancake are both costume options that fit the same dim stage directions. Whatever costume you pick, the spin behavior adds a plot twist. Oumuamua was not spinning about a single, tidy axis. It was in non-principal axis rotation, astronomy's euphemism for tumbling. Picture a poorly thrown football wobbling as it flies. That wobble is not random noise. It is a coherent, compound motion in which the object precesses, nutates, and rotates all at once. For rigid bodies, the spin settles along the axis with the largest moment of inertia. But if the object has been torqued recently or is irregular enough, damped stability can be delayed for a very long time. In cold space, without significant internal friction, that tumble can persist for millions of years. Oumuamua's light curve was so irregular in phase and period that a simple one-axis, one-period model failed. The fits worked only when you let the object wobble. What does tumbling tell us about the interior? One clue: if this were a loose rubble pile, certain fast rotations would tear it apart, unless it had cohesion beyond simple gravity. Oumuamua's inferred average rotation period on the order of hours, not minutes, does not demand superhero materials, but coupled with the huge shape factor, it nudges us toward an object with some tensile strength or at least a monolithic core. Non-principal axis rotation also acts like a stress test. Internal friction would gradually convert the chaotic wobble into a simple spin, bleeding energy as heat. The fact that it remained in a complex state when we saw it suggests either low internal damping, stiff material, voids, or both, or that it was excited into tumbling not too long before we met it, by a collision, by torques, during ejection from its home system, or by asymmetric activity after it came under our sun's light. Surface texture matters too. A uniform, matte rock and a patchy, icy shard with bright and dark regions will produce different light curves even with the same silhouette. The tenfold swing we saw could come from extreme shape, extreme albedo contrast, or a bit of both. Think checkerboard versus solid color. The checkerboard will flash as different panels rotate into view. Because we could not resolve the surface, we have to let multiple solutions survive. That is not a cop-out. It is exactly how inverse problems work. Many physical models can produce similar data, and you prune with additional constraints. Here, the constraints were poor. Oumuamua was fading as we learned about it, so the family of allowed shapes stayed large enough to include pancake, cigar, and splinter from something bigger. The tumble also invites a forensic timeline. Suppose Oumuamua began life as a more ordinary chunk in a young planetary system. Gravitational kickouts can jolt spin states. Low-speed collisions can produce elongated fragments with excited rotations. Thermal stresses can fracture and reshape over time. Toss in occasional torques from outgassing or subtle radiation effects, and the spin can wander across a landscape of states before freezing into the odd wobble we observed. None of this requires an exotic composition. It requires time, irregularity, and a few decisive nudges. Space's favorite recipe. What about centrifugal limits? How fast is too fast? The breakup threshold for a strengthless body depends on density and shape, but for objects 100 meters across, you usually need periods of a few minutes to fling material. Hours-long rotation, even for an elongated shard, is generally survivable. If Oumuamua is compact or has some cohesive bonding between grains, the safety margin widens. The awkward potato can wobble without flying into confetti. Here is the humility part. The light curve is a narrow keyhole. We do not get to walk around the object with a flashlight and say, "Ah, there's the dent." Instead, we read the strobe pattern and reverse engineer the dancer. That is why the sketches proliferated. Each is an honest attempt to square a loud brightness modulation with an inconsistent beat. The better takeaway is methodological. Shape and spin are not ornaments. They are dynamical fingerprints. They whisper about internal structure, past talks, and how an object holds itself together during violent chapters. In a universe that will not let us touch most things, rotation is a handshake we can actually feel through photons. Next, we switch from spinning rocks to the atmosphere they sometimes grow, the hazy Comet sweeping tails that turn cold nuclei into attention-grabbing comets, and the awkward silence when one of our visitors refuses to put on the neon sign. Comet are a comet's neon sign. Oumuamua left the open sign unplugged. Start with the basics. A comet's nucleus is a compact mix of ices and dust. Far from the sun, that mixture is fridge-stable. Closer in, sunlight turns the thermostat to who approved this, and volatile ices begin to sublimate, solid straight to gas. Escaping gas seeps through pores and cracks, drags dust grains off the surface, and inflates a thin, roughly spherical atmosphere around the nucleus. That atmosphere is the coma. It is not smoke, it is a colossal whisper-like cloud, so tenuous you could fit a person inside it and feel nothing but existential awe. The coma is where photons and molecules mingle, where sunlight pumps energy into freshly freed gases and makes them glow. In other words, it is the billboard that says, "Yes, I am a comet, and I am currently doing comet things." Once gas escapes the nucleus, two distinct highways emerge. Dust grains, pushed by sunlight and nudged by their own inertia, spread into a broad, curved tail that roughly follows the orbit. This is the photogenic, sunlit fan we all doodled in grade school. Plasma, on the other hand, has stage directions from the solar wind. Ionized molecules get swept backward along magnetic field lines, forming a narrow, often straight bluish tail that points almost directly away from the sun. The two tails are cousins with different temperaments, one graceful and dusty, one nervous and electrified. Both trace physics written in photons and fields. And what about that striking green many comets show near the head? That glow usually comes from diatomic carbon, C2, fluorescing in sunlight, the so-called swan bands in the green part of the spectrum. You make C2 by breaking larger, carbon-rich parent molecules apart under ultraviolet light. The fragments get pumped by solar radiation and re-emit at characteristic wavelengths. Your camera calls emerald. Here is the fun quirk. C2 has a short photochemical lifetime, so the green is strongest close to the nucleus and tends to fade before it can paint long tails. That is why comets often look like they are wearing a lime green scarf wrapped tight, not an all-green train stretching for millions of kilometers. Sometimes you also see a contribution from oxygen's forbidden line near the same color family, produced when sunlight knocks water apart and leaves oxygen atoms in an excited state. But C2 is the headliner for that neon look. Now, let us place our three celebrities on this stage. 3I Borisov behaved like an instructor's solution key, coma on, tails on, chemistry lighting up the spectrographs, and evolving activity as solar heating rose and fell. Dust production and gas species followed patterns we know from comets that formed here, even as the detailed mixture told us it hailed from colder storage. Visually, it ticked the boxes you expect from a nucleus that still carries volatile inventory on or near the surface. Its coma helped observers track changes over weeks, revealing a living, breathing object rather than a silent boulder. 3IATLAS presents a subtler profile, a faint coma right out of the gate, and hints of that greenish tinge you expect from active carbon chemistry. Faint does not mean unimportant. It means the balance between sunlight, surface composition, and surface area favors a modest flow. If C2 is present, the green halo is a photochemical handshake, sunlight carving parent molecules into smaller fragments, and those fragments returning the favor by fluorescing. For a new interstellar visitor, even a whisper of coma is gold, because it lets us sample composition through spectroscopy instead of guessing from reflected sunlight alone. Quiet coma are still fluent. Oumuamua, by contrast, ghosted the entire party. No obvious dust, no classic gas signatures, no bright halo. It raced through the zone where comets usually fog up and mostly stayed matte. There are several ways to pull off that vanishing act. One is inventory. If near-surface volatiles are depleted or locked beneath a crust of sun-baked, carbon-rich material, heat might not reach fresh ice fast enough to drive a visible coma. Another is grain size. You can leak gas without lifting much dust. Gas alone is hard to spot in faint, rapid overflights, unless it carries the right fluorescent molecules at detectable levels. A third is geometry and timing. A small, fast, dark object can cross our field of view before our instruments gather enough photons to shout coma. Either way, the absence of a neon sign does not mean nothing happened. It means whatever happened stayed below our detection limits or favored invisible species. Space is great at frustrating the paparazzi. Why does coma brightness vary so wildly among ostensibly similar icy bodies? Think of a nucleus as a patchwork quilt of terrains. Some patches are fresh and porous, with sunlight liberating gas and dust like confetti. Other patches are sintered, compacted, or sealed by prior heating. They shrug off sunlight like a seasoned vampire and contribute little. Spin states matter. If the active region keeps going into shadow, the production rate hiccups. So does thermal inertia, how fast a surface heats and cools, and the depth of volatile layers. Even the season matters. A minor tilt can turn a polar cap of ice into the summer side for a few weeks and then switch it off. The coma is the sum of all these micro decisions written in physics. Chemically, a green coma is a confidence check that carbon-bearing parents are near the surface, ready to photo-dissociate into C2. But green is not a personality test. Two comets can both glow and still be very different under the hood. Parent molecules like C2H2, C2H thick, or more complex organics feed the same fluorescent child, and the precise balance among CO, CO2, and water controls where and when the show brightens. Temperature thresholds matter. CO wakes far from the sun, CO2 at moderate distances, water closer in. Swap the mixtures and you reschedule the performance. In the end, coma are less about fashion and more about thermodynamics and plumbing. Borisov had open pipes. 3IATLAS has a thin but telling trickle with a hint of lime, and Oumuamua kept its valves nearly shut, or at least so discreet we could not catch the mist. The absence of a coma is data, not a disappointment. It sharpens questions about crusts, pore networks, and volatile inventories, and it sets the stage for a deeper puzzle. If a visitor shows little visible exhaust, yet still wiggles off the gravity script, what invisible forces are at work? Next, we chase that mystery, tiny pushes that add up, by unpacking the non-gravitational nudges that turned one visitor into a physics riddle and taught us how subtle outgassing can masquerade as a magic trick. Physics says no free lunches. Oumuamua insists it paid with store credit. Start with how the mystery push is even noticed. You fit an orbit using only gravity from the sun, the planets, the big asteroids, and watch how the predicted positions line up with the measured ones. For most small bodies, the agreement is gratifyingly boring. With Oumuamua, the residuals refuse to sit still. Night after night, the track whispered, "Something else is nudging me." The extra acceleration was tiny. Think a few parts per million of the sun's pull, but consistently directed away from the sun and fading with distance. That pattern is the telltale silhouette of non-gravitational forces. Comets often show this behavior, and the usual culprit is outgassing. Sunlight warms the surface, buried ices sublimate, and the escaping gas jets act like miniature thrusters. Nozzles are optional, pores and fractures do the job. If activity is stronger on the sunlit side, the net push point's roughly anti-solar, and as the comet recedes and cools, the thrust dwindles. When orbit fitters add a standard comet law term that scales with heliocentric distance, the math stops complaining and the residuals calm down. That is the familiar playbook. Oumuamua complicated the play. It showed the push, but not the parade. No obvious dust tail, no bright coma. If outgassing was at work, it either lofted very little dust, or the gas species were ones our hurried spectra could not easily catch, or both. One possibility is that the propellant was dominated by supervolatiles, carbon monoxide, or carbon dioxide, that can flow without dragging much grit. Another idea is a sun-baked crust hiding water ice beneath. Gas could percolate through a maze of pores, bleed into space, and still fail to produce a flashy halo. Outgassing does not owe us a light show. It owes us momentum, and momentum transfers silently. A second family of explanations leans toward radiation pressure, the gentle shove from sunlight itself. Every photon carries a smidge of momentum. Reflect enough of them, and the smidge adds up. For ordinary rocks, the effect is puny. To get Oumuamua's recorded nudge from light alone, you need an extremely high area-to-mass ratio. There are two broad ways to get that. Make the object very thin, cue the sheet and flapjack speculations, or make it extremely porous, a sort of cosmic aerogel with lots of surface and very little mass. In both cases, you end up with something that sunlight can bully more than gravity expects. The radiation pressure idea is appealing because the observed acceleration faded roughly like 1 over the distance squared, the same way sunlight dims. But it demands a structure that is either surprisingly delicate or surprisingly reflective. And then you have to argue it could survive interstellar travel without being shredded by dust impacts and cosmic ray chemistry. Possible? Yes. Comfortable? That depends on your taste in exotic souvenirs. A third path tries to split the difference. A fluffy, fractal aggregate with icy bonding. Picture a snowflake built from dust, more void than solid. Light enough to feel radiation pressure, yet icy enough to lose mass gently and keep the anti-solar push in character. This sort of object could be a shard from the outer skin of a larger body, or a fragile piece born in a cold disk and later flung into the void. It dodges some of the paper-thin sail worries while still giving photons leverage. The open question is durability. Does such fluff survive millions of years of micrometeoroid peppering? If it does, sunlight has something to grip. Torque is the detective we rarely invite, but always need. Outgassing jets not only push, they twist. If Oumuamua's thrust came from one-sided vents, we would expect its rotation state to evolve measurably. Period changes, precession rate drifts. The data window was short, and the tumble complicated, so the constraints are fuzzy. We did not catch a dramatic spin-up, but absence of a headline is not absence of a talk. It is just what happens when your subject fades by the week. Radiation pressure, by contrast, gives almost pure translation if the body is reasonably symmetric. Talks from light are tiny unless the shape is wildly lopsided, so a clear timed spin change would have favored outgassing. A quiet spin story keeps both camps alive. Thermal physics also sneaks into the case file. If sublimation drives the push, it should respond to the day-night cycle, lagging afternoon style, as heat percolates into the skin and escapes. That can tilt the thrust direction slightly off the pure anti-solar line, and fitters can look for that pattern. If radiation pressure dominates, the direction stays cleanly away from the sun. Oumuamua's residuals were broadly consistent with an anti-solar bias, but not diagnostic enough to plant a flag. In other words, the footprints are there, but the sand is wind-streaked. Contrast this with 3I Borisov, which did what comets are paid to do. Its coma announced vigorous activity, and small non-gravitational parameters showed up right where you expect them. Model the thrust with a standard sublimation law, and the orbit behaves. No sleight of hand, no philosophical crisis, just gas, dust, and momentum doing Newtonian chores. With Borisov, the astrophysics class could put down the chalk and say, see, this is the normal case. Where does 3IATLAS sit on this spectrum? Early views showed a faint coma and hints of carbon chemistry, so modest outgassing is in play. The betting line says we will measure small non-gravitational terms, that rise toward the sun and fall after perihelion, possibly with a flavor that reflects carbon dioxide, waking up earlier than water ice. But small and early are the operative words. The right answer for an orbit is earned, not assumed. You watch the residuals, you try the simplest physical model, and you upgrade only if the data force your hand. If 3IATLAS sticks to the Comet script, terrific. One more data point for interstellar often looks familiar. If it deviates, we sharpen the pencils. The larger lesson is methodological. Gravity gives you the headline path. Tiny forces write the footnotes. Learn to read the footnotes and you get surface clues without ever seeing the surface. Porosity from radiation pressure sensitivity, vent geometry from torque signatures, volatile inventory from how the thrust waxes and wanes with sunlight. That is the bargain in this detective story. We cannot fly alongside most visitors, but they leave momentum receipts. Next, we open the chemistry drawer. What the molecules themselves, water, carbon monoxide, carbon dioxide, and their photochemical cousins can reveal about where these travelers were frozen into being in the first place. Borisov isn't just icy, it's the cosmic equivalent of ordering a drink extra CO. Hold the water. If you want to read a comet's backstory, you do not start with its shape, you start with its pantry. Different ices wake up at different temperatures, so the mix of gases escaping a nucleus acts like a return address stamped in thermodynamics. 3 players matter most for quick chemical biographies: water, the homebody that needs comparatively warm sunlight to sublimate; carbon dioxide, the early riser; and carbon monoxide, the insomniac that can get moving in deep cold, where a nucleus formed relative to the snow lines for these ices, roughly the orbital distances in a young disk, where each species can freeze and persist, sets the initial inventory. Later, ejection into interstellar space freezes the story in place, like a cryogenic filing system with very slow clerks. Enter 2I Borisov, the show-off, when astronomers pried into its gas with the Atacama Large Millimeter (SAP-millimeter) array. They found carbon monoxide, far above garden variety levels, 9 to 26 times higher than typical comets seen at similar sun distances. That is not seasoning, that is a marinade. The result implies formation in a part of its natal disk cold enough to lock in abundant CO, with temperatures down near minus 250 degrees Celsius, territory where water is not the boss and carbon chemistry holds the remote. If you want a mental picture, think of a freezer so cold that the peas have frostbite, and even the freezer burns. This is evidence, not rumor. ALMA's spectra lit up with CO while more familiar traces sat at pedestrian levels, and NASA's write-up called it out as higher than anyone had detected in any comet at similar heliocentric distances. In other words, welcome to the CO district. Now swivel to 3IATLAS, the newcomer that decided to major in carbon dioxide. Early space-based spectroscopy reports flagged an unusually CO2-rich coma with water either faint or lagging. That balance tells a different formation tale. CO2 condenses and persists at temperatures warmer than CO, but still far colder than water's comfort zone. If a nucleus forms near the CO2 snowline and then gets stored in chilly exile, it will arrive with a pantry where CO2 is easy to liberate at modest sunlight, while water stays locked until later, or not much at all, if the outer layers are processed into a crust. Observers using NASA's CEPHREX mission highlighted a robust CO2 fog around 3IATLAS and direct evidence of water ice in the nucleus, sketching the portrait of an object that was well baked and boiled before ejection and is now venting the early waking volatile first. Subsequent summaries, including JWST follow-ups folded into community compilations, reinforced that CO2 forward signature. Translation: this comet's first language is carbon dioxide, with water speaking softly from beneath. Oumuamua, characteristically, refused to hand over a clean chemical ledger. Spectra and colors indicated a reddish surface, classic space weathering from long irradiation by cosmic rays. Irradiation can crack molecules, weld carbon skins, and make the topmost layer darker and tougher, sealing volatile reservoirs beneath a veneer that behaves like a thermal raincoat. That crust helps explain how an object exposed to the sun did not flaunt the usual water or dust signatures. It could also skew any trickle of escaping gas towards species that percolate through pores rather than explode into camera-friendly fountains. Over hundreds of millions of years, space can turn even an ordinary surface into a reluctant storyteller. The reddish tint is the autograph of that long, slow edit. So what do these ice preferences say about birthplaces? In young protoplanetary disks, temperature and pressure fall with distance from the star. Water freezes relatively close in, carbon dioxide farther out, and carbon monoxide at the far, far fridge end. If you assemble a nucleus beyond the CO2 line, you stock up on CO2. Beyond the CO line, you can hoard CO as well. Stir in local disk quirks, radiation fields, mixing and chemistry on dust-grained surfaces, and you get regional flavors. Borisov's CO bender points to origin zones where CO ice is abundant. Think mid-plane provinces colder than a penguin's mortgage. 3IATLAS's CO2 vigor hints at a slightly warmer, still frigid district, cold enough to bank CO2, not cold enough or not preserved enough to leave CO front and center. Oumuamua's weathered skin whispers, inventory present but shielded, or inventory long gone from the surface, which makes its deeper layers an open question with a locked door. If that sounds tidy, the caveats keep it honest. Chemistry is a historian, not a camera. A nucleus can migrate within its natal disk before ejection, cruising across multiple snow lines and remixing its pantry. After escape, cosmic rays keep writing on the cover page, and when the traveler finally meets our sun, the first volatiles to vent may not represent the whole stockroom, just the shelves nearest the door. That is why absolute ratios CO to CO2 to water have to be read alongside context. How fast the object is heating, how porous the crust is, and how much of the surface is actually active. Still, patterns matter. CO-heavy chemistry, like Borisov's, underscores that some planetary systems stash material in ultra-cold freezers and then fling it wholesale. That is a formation environment compatible with disks, where outer regions are dense and shadowed enough to keep CO solid, or where fragments of CO-rich dwarf planet crust get liberated by collisions and tossed into space. CO2-rich signatures like 3IATLAS's point to storage in zones that are cold but not extreme. They also hint at earlier thermal episodes that selectively cooked off CO or sealed water beneath the skin. If and when water ramps up later for 3IATLAS, that timing will refine the depth of its ice layers and the thickness of any insulating crust, like learning whether the freezer door was left ajar for a geologic minute. Why should any of this make you grin? Because the galaxy is serving us a tasting menu. Borisov tells us that CO-loaded kitchens exist and can season comets far beyond what our local cookbook predicted. 3IATLAS says CO2-forward recipes are on the table too, perhaps the norm in some neighborhoods. Oumuamua reminds us that the waiter may arrive with the dish under a lid, daring us to infer ingredients from the aroma of whatever leaks out. Chemically, these three do not cancel each other. They triangulate, and with each measurement, planet formation shifts from a single origin story to a buffet of regional specialties. As we fold the menus, remember the punchline. Ice lines are less like fences and more like food trucks, shifty, responsive to local weather, and critical to what gets served. Our visitors just handed us receipts from other star systems. Next, we will explore where those receipts were printed, source regions, and ejection mechanics, and why the galaxy's lost and found bin never seems to run out. These objects are the postcards exoplanet systems forgot to mail. Picture a young planetary system as a crowded rink, newborn planets carving lanes, smaller icy bodies ricocheting off gravitational elbows, and a star in the middle keeping score. In that chaos, some fragments get an especially brisk shove. If the push is strong enough, they are not merely tossed to the outskirts, they clear the stadium and keep gliding between stars. The usual culprits are giant planets. Big worlds act like bouncers with physics degrees. Close encounters trade energy and momentum, and a fraction of planetesimals are launched above local escape speed, becoming interstellar debris. Theory and reviews point to a simple rule of thumb. Only hefty planets can eject efficiently. Think giant planets rather than terrestrials. So systems with Jupiters, hot or cold, are prime factories for flinging small bodies into the galaxy. How much the galaxy contributes also depends on architecture. Put one or more giant planets on crossing or resonant orbits, and you get a long ejection season. Migrate those giants, and you can stir the disk so thoroughly that excess carryout becomes inevitable. Add in rare but potent events like stellar flybys, while a system is still in its crowded birth cluster, and you can spike the ejection rate for a few million years, spraying fragments with modest interstellar speeds. The literature suggests that even a percent-level leakage of planetesimals over a system's youth adds up to a galactic background of drifters, because there are so many planetary systems running the experiment in parallel. In other words, the Milky Way is a shared conveyor belt for everyone's leftovers. Galactic dynamics then turns local flings into long-haul journeys. Once free of their parent stars, these bodies join the general stellar traffic, governed by the galaxy's gravity. Their paths are not laser straight. They bob in the disk's potential and get tiny tugs from passing stars and molecular clouds. Statistically, though, you can forecast which directions our solar system is more likely to meet them from. Because the sun is plowing through its neighborhood, there is an upwind direction called the solar apex, akin to the front windshield on a moving car. If interstellar debris is sprinkled through space, we should meet more of it from near that point. Oumuamua's inbound radiant came within a few degrees of that apex, the orbital equivalent of bugs on the windshield. A tidy match to expectation. Now put 3IATLAS into this map. Its approach is from the neighborhood of Sagittarius, roughly toward the Milky Way's crowded central backdrop, and well placed for southern observatories to pounce quickly. That southerly arrival is scientifically useful for two reasons. First, it widens the sample of inbound directions, reminding us that although apex paths are probable, the galaxy is three-dimensional and our incoming lane is not a single narrow corridor. Second, it highlights survey bias. For the last decade, many of the most productive wide-field surveys lived in Hawaii and the continental US, tilting discovery toward northern skies, with ATLAS now operating from Chile too, and southern heavyweights like ESO's VLT snapping early images. We are filling in coverage that was thinner below the celestial equator. The more symmetric the patrol, the less we will mistake telescope geography for astrophysics. Why do the source regions matter beyond trivia? Because chemistry, size, and spin all trace back to where and how each body formed before its eviction. If a fragment was born beyond the carbon monoxide snow line in a cold midplane, it will carry a different inventory than one assembled just beyond the carbon dioxide line. If it was chipped off a dwarf planet crust in a smash-up, its porosity and strength may depart from primordial fluff. When a giant planet kicks such pieces out, they leave carrying the fingerprints of their nursery and millions of years of interstellar exposure, then scribble additional notes on the cover. Irradiation reddens surfaces, micrometeoroids sand them down, and ultravolatiles may vanish from the skin. The path to our telescopes is therefore a two-act story, formation plus weathering, with the ejection providing the pivot. There is also a demographic angle. Some models argue that a small fraction of systems, those with unstable or tightly packed giant planets, do most of the ejection, supplying the lion's share of interstellar small bodies. Others emphasize that flybys in stellar birth clusters can mass-produce drifters even from otherwise calm systems. Either way, the expected interstellar population is not monolithic. We should encounter everything from textbook comets to low-activity shards, and their arrival directions should sample the sky broadly with a statistical nudge toward the apex, not a monopoly. Oumuamua, near the apex, and Borisov from a high-latitude fit that mixed picture. 3IATLAS arriving from the Sagittarius side keeps us honest about the sky's southern half. Survey strategy translates these dynamics into detections or misses. Depth finds the faint, cadence finds the fast, latitude finds your hemisphere. Historically, the northern bias meant we were exquisitely sensitive to some approach vectors and less so to others. The expansion of the Atlas network into the southern hemisphere and routine follow-up from Chilean facilities chip away at that imbalance. If the stream of future interstellar finds starts to look more isotropic as southern coverage improves, we will know that earlier patterns were partly our own footprint showing through. If instead, a real excess persists near the apex even with balanced sky patrols, that will be a satisfying confirmation of the headwind logic. The outcome teaches us something we could not learn from one or two visitors. Finally, what does all this say about the particular postcards we have in hand? Oumuamua's near-apex arrival fits the broad prediction for randomly distributed debris carried along by the sun's motion. Borisov's different geometry underscores that there is no single superhighway, just many lanes feeding the inner system from all sides. And 3IATLAS, with its southern sky debut and Sagittarius backdrop, is our reminder that instruments placed under different skies reveal different stories. 3 objects do not make a full census, but they already show that the galaxy's lost and found is richly stocked and directionally diverse. Keep enlarging the net, especially below the equator, and we will trade anecdotes for statistics. Next, we zoom out from origins to infrastructure, how our modern surveys, pipelines, and observatories evolved to catch such fast strangers in the first place, and what the next generation will add to the watch. The universe didn't get busier. We finally installed better doorbells. If you rewind to the mid-2000s, wide-field astronomy was already dreaming big, but the hardware and software were still stretching into their roles. Fast forward to the late 2010s and mid-2020s, and you get the perfect storm for catching brief, faint, fast visitors, giant digital eyes, smarter algorithms, and a follow-up network that behaves more like a relay team than a collection of solo runners. Interstellar finds look sudden only because our motion sensors started sampling the sky often enough and deep enough that a 100-meter rock on a hyperbolic sprint can't slip through the cracks anymore. Start with the eyes. Modern survey cameras went from many megapixels to bring your own power plant. Gigapixel mosaics, paired with wide optics, let a single exposure swallow a large swath of sky. And the sensors are exquisitely linear and low noise. In 2017, Pan-STARRS was already operating at this scale, mapping the heavens with a cadence good enough to build a nightly memory of what's new. By 2019, the broader time domain ecosystem, additional surveys, sharper pipelines, and more aggressive transient brokers was in high gear. By 2025, southern installations of all sky systems, including Atlas's Chile node, and refined software, put the final polish on Don't Blink patrols. The hardware trajectory is simple: larger field, lower noise, faster readouts, and more nights on sky. The result is unromantic and glorious. More photons in, more often. But the quiet revolution is software. The workflow that turns raw images into this dot moved has become industrial. Precise calibrations, astrometric solutions that pin stars to the sky with milliarc-second confidence, image differencing that subtracts last night from tonight to expose the mischief, and machine learning filters that toss out cosmic rays, ghost reflections, satellites, and the occasional insect cameo. After that first culling, tracklet linkage stitches multiple detections into coherent paths, and orbit solvers flag anything that refuses to behave like a slow, bound resident. In 2017, these tools were already effective. By 2019, they were faster, cleaner, and more automated. By 2025, they can promote an oddball candidate from whom to page everyone before sunrise. Speed matters because interstellar candidates do not loiter. A typical pipeline now shrinks the time from shutter click to community alert to hours or less, with standardized formats that telescopes and humans can read without translation. The moment a candidate looks interesting, it is shipped to the Minor Planet Center, stamped with a provisional designation, and blasted to a global audience of observers who can pivot immediately. The alchemy is not just computation, it is choreography. That choreography is our second superpower. Follow-up used to mean phone calls and good luck. Today, it is robotic cues, target of opportunity triggers, and a globally distributed set of medium telescopes ready to pounce. Facilities in Hawaii, the continental US, Europe, South Africa, Australia, and Chile hand off targets as Earth rotates, keeping the clock running on light curves and spectra. Small and mid-sized telescopes shine here. They can track a magnitude-teen speck with ridiculous flexibility, and their time is not booked years in advance. Larger observatories step in for spectroscopy and deeper imaging once the coordinates are nailed. Think newsroom, on deadline. Someone writes the leady, someone checks the quotes, someone pulls the archival file, and the editor makes sure it all lands on the front page before the object fades. Now a quick time capsule. In 2017, we had strong surveys. Hello, pan-stars. Mature but not omnipresent machine vetting, and a follow-up culture that could spin up quickly when something weird appeared. That was enough to notice a faint, fast intruder after perihelion and still salvage a parade of measurements. By 2019, the community had tightened its reflexes. Faster candidate promotion, more brokers routing alerts, and more southern participation. As a result, when a visitor arrived with a bright coma, we turned spectroscopy and imaging on almost immediately and rode the activity for months. By 2025, all sky systems operating in both hemispheres with multiple passes per night gave us earlier detection windows and better geometry coverage. Improved classifiers, reduced false positives, and rapid response spectroscopy captured volatile fingerprints before they diluted. The direction of travel is clear: shorter latency, denser cadence, and smarter triage. And just over the horizon, Rubin Observatory's Legacy Survey of Space and Time, LSST, changes the scale from busy to fire hose. A giant field of view married to a large mirror means routine visits to faint magnitudes across the whole southern sky. The cadence is designed for transients and movers, with on-the-fly difference imaging, and an alert stream so large it demands automated brokers by design. For interstellar interlopers, that means earlier discovery at larger distances, when they are still bright enough for high-quality spectra, and before geometry turns awkward. It also means statistics, not one object every few years, but a growing sample large enough to ask population questions. How common are coma-quiet shards versus textbook comets? Whether inbound directions truly cluster near the solar apex once survey bias is flattened, and how the distribution of brightness and speed maps to source environments. None of this implies that heroics are obsolete. Weather still ruins nights, satellites still photobomb, and some targets stubbornly hide behind the sun when you most want them. But the batting average has changed. When a fast, hyperbolic speck enters stage left, we are now likelier to catch it on the way in, measure it while it is still bright, and keep watching long enough to squeeze out shape, spin, and chemistry. The technology timing is not about a single telescope or software trick. It is about a stack, sensors that do not blink, pipelines that do not nap, and a network that treats every alert like a baton pass rather than a shrug. So yes, the universe has always been throwing pebbles through our yard. We just upgraded from a peephole to a glass wall, added motion lights, and told our friends to text when they see footprints. Next, we will put those upgraded sensors to work on the nitty-gritty of observing fast, faint targets. How to wring information out of a handful of photons without making your telescope cry. Astronomy, where bright means maybe your telescope won't cry tonight. Interstellar visitors are the definition of difficult targets. They are dim, they are quick, and they do not hang around. Observationally, that is a triple espresso of headaches. First, the short arc problem. You get only a few nights, sometimes a few hours of good geometry, to nail down a path before the object fades, dives behind moonlight, or sprints into a part of the sky your observatory cannot reach. Orbital fits love time. Interstellar objects are allergic to it. With only a sliver of trajectory measured, uncertainties puff up like a soufflé, and the difference between point here and point there can be a few telescope fields by the next dusk. The cure is cadence. Multiple measurements per night, across multiple longitudes, to stitch a line into a curve before the opportunity evaporates. Speed is the next gremlin. Many telescopes are designed to track the steady parade of stars, which politely drift at sidereal rate. A hyperbolic sprinter might slide several arcseconds per minute, meaning a normal exposure smears it into a stubby streak. Streaks are dramatic for posters and terrible for precision. Observers switch to non-sidereal tracking, telling the mount to chase the moving dot, and then keep exposures short enough that residual drift does not bloop the target into invisibility. Now flip perspectives. While the scope chases the rock, the stars streak. That is fine for astrometry, where you fit the moving dot, but it complicates photometry, measuring brightness because your reference stars have turned into noodles. People solve this with clever pipelines that denoodle the stars, or by alternating between sidereal and object tracking frames, accepting a hit in efficiency to keep the math sane. Then there is plain old faintness. Even a good interstellar catch may hover around magnitude 11 or 12 at its best, far from naked eye, challenging for small optics, and merciless to anything under a bright moon. For the uninitiated, magnitude is a logarithmic scale. Each step is a big change. Magnitude 12 is the difference between easy target for a decent backyard rig and are we sure there is something here? Photons dribble in. Rid noise, sky glow, and imperfect flats start arguing about who gets to ruin your measurement first. You mitigate with longer total integration times. Many shorter exposures co-added after shifting to the object's motion. That buys signal to noise at the cost of sleep. Astrometry versus photometry is the nightly trade. Astrometry pins the path. Photometry extracts light curves, colors, and activity hints. For interstellar objects, both are essential and both are fragile. A handful of precise positions early on shrinks the search box for everyone else. A handful of well-calibrated brightness points prevents you from fooling yourself about shape or coma. The short arc pressure means observers often prioritize position measurements first. Get the orbit out of the danger zone, then layer photometry once pointing is safe for the herd. Now to the division of labor. Professionals and amateurs have converged into complementary roles that make the most of every clear patch of sky. Amateurs with modern CMOS cameras and half-meter class telescopes deliver astonishing astrometry and time series photometry, especially when the target sits in the magnitude 12 to 16 range. Their superpower is flexibility. They can pounce between midnight clouds, change filters on the fly, and stay on one object for hours without a committee meeting. Consortia of skilled amateurs keep coverage rolling as Earth turns, stitching together light curves that no single site could manage. On the professional side, small and mid-sized observatories are the workhorses for nightly tracking, often with instrument stability and calibration that squeeze down systematics. Large facilities, 8-meter class telescopes, and space observatories are the heavy artillery for spectroscopy and deep imaging once the orbit is secure. Spectroscopy is precious because it turns light into molecules and minerals. A spectrum can tell you whether carbon monoxide is playing lead guitar, whether carbon dioxide is whispering from the wings, or whether dust is scattering sunlight with a particular grain size distribution. But spectra are expensive in photon currency. Dispersing light across thousands of wavelength bins means each bin gets a thinner slice of signal. You need a bigger telescope, longer exposures, darker skies, or ideally, all three. Add the fast target tax. While your slit or fiber is lined up, the object is still moving. Miss the pointing by a little, and your spectrum becomes a spectrum of nothing, which is scientifically interesting only to philosophers. Timing makes spectroscopy even trickier. Gas species change with distance from the sun. Activity can flicker with rotation. Telluric absorption, our atmosphere's own spectral fingerprint, wanders with weather. The optimal moment might be a narrow wedge in time, when the object is high, the moon is down, and your instrument is actually available. That is why target of opportunity triggers exist, and why instrument teams sleep with their calendars on vibrate. A single successful spectrum can compress weeks of guessing into one evening of answers. Filters and colors offer a budget version of chemistry when full spectra are out of reach. Broad and narrowband photometry, through carefully chosen filters, can sniff out dust production, infer the presence of certain radicals, or at least flag whether the coma is dust or gas-dominated. It is not the same as resolving lines, but when the object sits at magnitude 14 and falling, a cleverly designed filter set can save the night. Think of it as speed dating for comets. Not a life story, but enough to know if you should schedule a second look. Calibration is the invisible backbone of all this. Flat fields remove pixel-to-pixel quirks, bias frames tame electronics, standard stars anchor your magnitudes and colors, astrometric catalogs prevent quiet milliarc-second disasters. For fast movers, even the timestamps matter. A sloppy clock can shift a measured position by more than your error budget, especially at high sky motion. Many teams now GPS discipline their observatory time or audit it obsessively. Nothing is less glamorous and more essential than correct time. Finally, a word about expectations. Not every night yields a light curve, with drama or a spectrum with fireworks. Sometimes the win is simply shrinking the positional uncertainty, so the next station can acquire the target in 2 minutes instead of 20. Sometimes it is setting an upper limit. No detectable coma above a given surface brightness, no measurable color slope beyond a certain value. For interstellar objects, even non-detections are decisions. They redraw the silhouette of what the object could be. So yes, in this game, bright often means my telescope won't cry. And even then you bring tissues. But when the photons land and the tracking holds, the payoff is disproportionate. A few hours of disciplined observing swap, guesswork for geometry, chemistry, and spin. Next, we leave the camera room for the lab bench and ask what dust and gas, when we do catch them, reveal about the nurseries these travelers fled. Comets are freezer-burned leftovers from the universe's meal prep. When we turn a spectrograph toward a visitor, we are essentially reading a grocery receipt that survived a very long walk home. Lines and bands in the spectrum correspond to specific molecules and minerals, and each has a comfort temperature. Match the menu to the thermostat, and you back out where, in a protoplanetary disk, that nucleus most likely formed. Start with the gases, the aroma wafting off the freezer box. Water is the late riser. In most disks, it only sublimates efficiently closer to the star, so strong water emission near the sun means accessible water ice in the shallow subsurface. Carbon dioxide wakes earlier. It is the friend who shows up before the party starts. If CO2 dominates the gas budget while water stays shy, the nucleus probably stockpiled volatiles in a region colder than water's snow line, but not so cold that CO rules. Carbon monoxide, by contrast, is the insomniac. It can stay solid at temperatures where water and CO2 long since gave up. So bright CO lines imply that parts of the nucleus formed, or at least were last reset, at very low temperatures. Think outer disk, midplanes, or shadowed niches where the star's heat barely whispers. The relative strength of these gases is a thermometer and a map rolled into one. Beyond the big three, the photochemical children, CN, C2, C3, NH, OH, add nuance. CN and C2, for example, are often produced when larger organic parents are cracked by sunlight. Their ratios hint at how carbon-rich those parents were and how exposed the near-surface layers have been. O is the reliable proxy for water. Hit H2O with ultraviolet light, and OH pops out, glowing in familiar lines that let us estimate water, even when the main band is hard to see. Blend these traces and you can tell whether a coma is gas-led, molecules driving the show, or dust-led, sunlight on grains doing most of the brightening, which in turn says something about pore networks and how easily gases can escape the crust. Dust is the second half of the story, the texture of the leftovers. At infrared wavelengths, silicates broadcast their identity with broad features near 10 and 18 microns. A smooth, rounded 10-micron bump suggests amorphous grains, glassy, quick-formed, never annealed by serious heat. Sharp substructure and extra contrast betray crystalline silicates, olivine and pyroxene, that have been heated and cooled in an orderly fashion. Crystals do not grow themselves in the deep freeze. They need inner disk temperatures or shock heating. So when we see crystalline fingerprints in dust coming off a cold, outer-borne nucleus, we learn that the nursery did some mixing. Grains cooked near the star were transported outward and blended into comet-making stock. A single spectrum becomes a postcard from a conveyor belt. Grain size leaves clues too. The slope of the reflected light spectrum, how red or neutral the object appears, depends on particle sizes and surface chemistry. Fine. Soot-like grains tend to redden light. Larger, pebble-scale grains flatten the color. Polarization measurements, where we examine how light waves line up after scattering off dust, add another dimension. Polarization increases with certain size ranges and surface roughness, letting us estimate whether the coma is full of airy fluff or compact chips. Combine color slopes, polarization curves, and how brightness changes with phase angle, and you sketch a size distribution rather than a guess. Is the coma dominated by submicron haze that sunlight can easily push into a broad fan, or by heavier grains that hug the nucleus and contribute to that dust jet look? The answer tells you about cohesion on the surface and the violence of the gas flow tearing grains free. Mineral ratios hint at birthplace chemistry. Magnesium-rich versus iron-rich silicates change the infrared profile. The presence of sulfides points to environments where sulfur remained in condensed form rather than ending up in gas phase molecules. Organics, complex carbon compounds that smear into broad spectral plateaus, speak to low-temperature chemistry on dust surfaces, where hydrogenation and radiation slowly assemble tarry coatings. These organics darken and redden surfaces, and when lofted, tint the dust's reflectance. In a lab, we watch ices and dust under ultraviolet lamps to see which combinations reproduce the colors and features we measure. In space, our spectra tell us which lab recipe the comet's chef chose. All of this ties back to protoplanetary disks, which are not serene pizza doughs, but weather systems. Picture a flared, gas-rich disk with temperature dropping outward and toward the midplane. Snow lines slice through it like isotherms. Inside one line, a molecule is vapor. Beyond it, the same molecule is ice. But these lines are not static. Disk luminosity, accretion bursts, and shadowing by puffed-up inner rims can shove them around by astronomical units. Pebbles drift inward, carrying ices, pressure bumps trap them, turbulence and disk winds loft material vertically and fling it radially. A nucleus assembled in such a pinball machine can inherit a messy blend. CO-rich ices from far out, crystals from way in, organics baked gently in between. Spectra are how we reverse engineer which lanes mattered most for a given object. Even isotopes whisper location and history. Deuterium to hydrogen ratios in water, when measurable, reflect formation temperatures and chemical pathways. Nitrogen isotopes in CN or HCN can point to interstellar inheritance versus disk-built chemistry. These measurements are hard at the faint end, but when they land, they pin the timeline. Some fraction of a comet's chemistry may predate the star itself, preserved from the molecular cloud. Another fraction is distinctly local, cooked in the disk's reactive kitchens. The gas-to-dust ratio is the final seasoning. Gas-rich Comet tell us vents are efficient and volatile layers are shallow. Dust-rich Comet imply crustier surfaces or larger grains, decoupling from the gas flow. In population studies, those ratios cluster into families, some depleted in carbon chain species, some not, suggesting distinct regions or epochs of assembly. For interstellar visitors, falling into one family or another is a strong hint that other planetary systems run similar kitchens, with comparable shelves and freezers. Put simply, spectra and dust diagnostics turn a fleeting blur into a birth certificate. CO-rich, you are likely a child of the deep cold. CO2 forward with timid water, you were assembled where the freezer door was cool but not frigid. Crystalline silicates in a dusty coma, your nursery mixed inner disk and outer disk goods like a chef who ignores the local ingredients only sign. None of this requires touching the nucleus. We let starlight do the heating, molecules do the talking, and minerals do the autographing. Next, we will set the chemistry aside and talk about the human chemistry, how wild headlines and tidy data collide whenever a strange rock flies by, and how to keep curiosity sharp without letting speculation outrun the evidence. Aliens might be out there, but interstellar comets are not their rideshare receipts. Every time a fast, faint stranger cruises through the inner solar system, the internet does what it does best. It invents plot lines faster than the data arrive. Think pieces sprout like mushrooms after rain, mysterious, numerous, and occasionally poisonous. Oumuamua starred in the inaugural season, op-eds flirted with spacecraft scenarios, social feeds proposed solar sails, and memes declared it a cosmic USB stick ejected by a bored civilization. When 3IATLAS entered the chat, the sequel bait was irresistible. Surely the third interstellar visitor would deliver the twist, the telltale signal, the engineered geometry, the headline that writes itself, and yet the universe remains maddeningly literal. Most of the time, the data say small, natural, weird in ordinary ways, which is science's version of a polite shrug. Let us use the frenzy to sharpen skepticism rather than scold curiosity. The rule of thumb is simple. Extraordinary claims need extraordinary evidence, not ordinary inconvenience. A tiny mismatch between a simple model and a complex reality is not proof of design. It is proof that reality has more knobs. When a light curve refuses to fit your favorite shape, you do not summon starfarers. You summon better models for irregular surfaces and tumbling spins. When a trajectory needs a small non-gravitational term, you do not jump to megastructures. You check for invisible outgassing, radiation pressure sensitivity, thermal lag, or boring old calibration demons. Physics keeps many mundane rabbits in its hat. Bayesian thinking helps here without demanding a PhD. What is more likely a priori, that a 100-meter object, one of trillions roaming a galaxy, is a natural shard kicked free by planetary chaos? Or that it is an artifact of a technological species, drifting conveniently into our telescope's field of view at the very moment our surveys became competent? The prior for nature is enormous. The prior for deliberate tech is vanishingly small. To swing those odds, you need evidence with a lever arm to the moon repeated, unambiguous, multi-wavelength signatures that scream machined, powered, commanded. Weak, single-channel oddities do not move the needle. They mostly move headlines. Media dynamics amplify the problem because mystery sells faster than nuance. No obvious coma morphs into impossible by natural means. Unusual chemistry becomes alien recipe. But absence of a detection is not proof of absence. It might be proof of your instrument's limits, your timing, or your atmosphere's mood swings. Skepticism is not cynicism. It is quality control. When a claim leans on a subtraction, we didn't see X. Cross-examine how hard anyone looked, with which tools, and for how long. The universe is vast. Our exposure time is short. Memes, for their part, are both the problem and the antidote. They spread speculation like glitter, and at the same time, give science a chance to smuggle in context. A great meme with the right caption can correct a misconception faster than a sober thread of equations. No, it's not a spacecraft, it's a rock with commitment issues. Humor works because it lowers the drawbridge. People will share a joke they would never share as a PDF. The alien hypothesis is not taboo, it is just expensive. If you assert intent, steering, signaling, engineering, you sign up for receipts. Periodic transmissions across bands, thermal behavior that violates passive heating, decelerations that cannot be explained by jets or light, geometry that updates with purpose rather than physics. Natural explanations have to clear hurdles too, but those hurdles are well worn. Sublimation laws, surface roughness, fractal porosity, radiation pressure, thermal recoil. Before leaping the fence into ET built this, you must exhaust the garden of earthly, cosmic delights. A useful mental check is the multiplicity test. If a phenomenon pops up in one dataset and vanishes in others, be cautious. If it appears across independent telescopes, wavelengths, and teams, breathe easier. With interstellar visitors, we often have thin coverage, short arcs, fading magnitudes, frantic schedules. That thinness is fertile soil for overinterpretation. A single odd residual in a single night can be a wind gust. You wait to see the weather. Another check is mechanism humility. Our instruments do things we forget to imagine. Shutters vibrate, detectors saturate, pipelines misclassify streaks, and human brains seek patterns where none exist. The universe does not conspire to fool us. Our gear conspires to be itself. Scientists treat anomalies as invitations to audit everything, from the telescope's heartbeat to the code's defaults, before rewriting the cosmos. It is not lack of imagination, it is respect for the trickster spirit of measurement. So how do we engage the public without dampening the thrill? By narrating the chase, not just the verdict. Explain what would count as decisive evidence for an artifact. Steady, narrowband radio lines that Doppler track the object, thermal excesses inconsistent with sunlight, thrust patterns that follow a schedule, not a solar vector. Then show what we actually saw, a faint tumbling point with a light curve that screams awkward potato, a small outward push consistent with physics we already know, and chemistry that says freezer, not factory. Curiosity survives the downgrade. It just lands on firmer ground. Finally, remember that not aliens is not a consolation prize. Nature routinely outweirds our first drafts. A CO-soaked interstellar snowball, a CO2 forward drifter with timid water, a crusted shard that shrugs off the sun. Each is a plot twist, just not the one with a press conference. Save the champagne for the day we catch a light that blinks prime numbers. Meanwhile, celebrate the quieter miracle. Our species can spot a 100-meter traveler crossing a billion-kilometer stage and infer its birthplace from a few photons. As flexes go, that is up there. Next, we pivot from headlines to hardware and talk about the mission idea built for exactly this kind of surprise. A spacecraft waiting in ambush, ready to sprint toward a newly discovered visitor, the moment the galaxy drops another postcard in our mailbox. Think of it as cosmic birdwatching, but the bird is moving at 60 kilometers/s and hates appointments. Most spacecraft launch knowing exactly which target they will meet. Comet Interceptor flips the script. ESA and JAXA are building a 3-spacecraft ambush that will launch to the Sun-Earth L2 region and wait, yes wait, for a pristine long-period comet or even an interstellar visitor to wander within reach. L2 is not a parking lot in the literal sense, but it is a gravitationally convenient cul-de-sac, thermally stable, always in step with Earth for communications, and close enough that a timely push can send the mission on a tailored intercept. The plan is simple to say and hard to do. Sit quietly for a few years, then sprint. 3 spacecraft is not marketing flourish. It is the reason this can work at extreme flyby speeds. The main craft, often called Spacecraft A, carries remote sensing cameras and thermal/IR spectrometers, plus dust fields and plasma packages to map the environment from a safer standoff distance. Shortly before closest approach, it releases 2 smaller probes, B1, a JAXA contribution, and B2, an ESA contribution. Each flies a different trajectory through the coma, sampling different plasma and dust conditions, and imaging from distinct angles. The choreography turns a single blink and you miss it pass into a multi-point 3D experiment. Nucleus context from A, close-up geometry from B2's images, hydrogen and plasma perspectives from B1, and simultaneous in-situ measurements across the gas and dust. 1 pass, 3 vantage points, because no one wants their once-in-history comet in flat 2D. Why the ambush posture? Fresh comets on their first dive toward the sun are usually discovered late, sometimes only months before perihelion. By the time we spot them, there is no chance to design, build, and launch a new mission. Parking Comet Interceptor at L2 buys the one thing we never have with rare targets: a head start. When surveys flag a reachable newcomer, controllers can compute a departure burn, pivot the stack off the halo orbit, and set up a high-speed flyby with pre-planned geometries for A, B1, and B2. It is the space equivalent of having your shoes on when the doorbell rings. The reachable part is not a hand wave, it is orbital accounting. From L2, the mission has a finite change in velocity budget, so target selection threads a needle, the right approach direction, the right timing, and a closure speed the sensors and shields can tolerate. Long-period comets are prime, but an interstellar target is explicitly in scope if its path and schedule match the fuel math. The waiting period is planned for roughly 2 to 4 years. If no worthy candidate shows, the team can keep listening or choose a backup from the best options on offer. The goal is a dynamically new comet that has not been cooked by many perihelion passages, or a true extrasolar interloper, chemically unedited postcards from faraway kitchens. Fast flybys demand specialization. At tens of kilometers per second, you do not sidle, you streak. That is why the payloads are tuned for brief exposures and rapid scanning. The instrument suite spans visible to thermal infrared imaging for nucleus shape, texture, and temperature, mass spectrometry for neutral and ion composition, and fields and plasma sensors for the solar wind wrestling match. Probe B2's OPIC and ENVIS cameras are designed to capture the near-nucleus geometry and the coma's global structure, while B1 contributes wide-angle and hydrogen imaging plus plasma diagnostics. Put the pieces together, and you can triangulate jets, reconstruct topography, and map how gas, dust, and magnetic fields braid around a sun-heated ice rock. And yes, there is shielding. Dust at 60 kilometers Ces is nature's sand blaster. Each element flies a slightly different corridor to balance science return against risk, and the hardware includes dust deflectors designed to survive the grit. The multi-probe design helps here too. The close-pass probe can brave higher risk for sharper science, while the main craft maintains a safer offset to guarantee the broader context. It is the planetary science version of do not put all your detectors in one basket. Rapid response is not only about propulsion, it is also about people and pipelines. The moment an appropriate candidate is announced by survey teams, the mission's ground segment must run trajectory, update navigation sequences, and crank through instrument scenarios, which filters, which exposure ladders, which scan patterns, which data priorities. Telecommands flow, rehearsals run on simulators, and the cruise becomes a sprint finish. The split craft approach actually simplifies the timeline in one way. B1 and B2 can be pre-scripted for if this, then that. Encounter geometries, with only final timing uplinked when the target's ephemeris is nailed. Think of it as loading your camera presets before the hummingbird enters the frame. Schedule-wise, Comet Interceptor is planned to launch in 2029 as a co-passenger with ESA's exoplanet mission Ariel on an Ariane 6. After delivery to L2, Ariel stays to study far-off worlds, while Comet Interceptor waits for a worldlet to come to it. The mission was selected in 2019 as an ESA fast class concept, formally adopted in 2022, and has been steadily moving through build and test, structures shaken, shields trialed, electronics delivered, international contributions slotted in. The through line is clear: keep the spacecraft agile, the probes light and capable, and the ground team ready to pivot when the sky offers that one perfect shot. If all goes to plan, the payoff is enormous. For a dynamically new comet, we get first-look nucleus geology and chemistry before solar baking scrubs away fragile clues. For an interstellar object, we get the first close images and in-situ measurements from a traveler that truly does not belong here. A lab on a flyby that can turn decades of inference into direct evidence. Either way, the mission trades waiting time for once only science. It is patience weaponized, and the joke writes itself. Comet Interceptor is the birder with binoculars already in hand, facing the right patch of sky, silently counting down. The bird may not be rare, it may be unprecedented. When it streaks across the field, 3 pairs of eyes move at once. Next, we switch from spacecraft choreography to data choreography, how scientists turn flickering photometry and uneven measurements into reliable shapes, spins, and models, so the story stays honest when the signal gets stingy. Data are shy, models are chatty, scientists play matchmaker. When a distant speck refuses to resolve into anything but a pixel and a whisper, astronomers lean on light curves and spectra the way detectives lean on alibis and receipts. A light curve is simply brightness versus time, but it hides an arsenal of clues. As a rotating body turns facets toward and away from the sun and earth, its reflected light rises and falls. The pattern encodes spin period, hints at elongation, and, if activity is present, betrays jets and dust that do not care about geometry. Spectra add the chemical accent, absorption, and emission features that shout silicate, ice, or organic gunk. The trick is disentangling signal from the many gremlins that mimic it: clouds, moonlight, detector quirks, and that most mischievous suspect of all small number statistics. First, size is slippery. Apparent brightness depends on both cross-section and reflectivity. A small, shiny object can look like a larger, soot-covered one. To break the degeneracy, we combine visible light with thermal infrared. The thermal flux depends on how much sunlight is absorbed and re-radiated, so pairing it with the reflected light constrains both size and albedo. Even then, you must assume a thermal model. How rough is the surface? How quickly does it conduct heat? How beamed is the emission? Change those knobs, and your inferred diameter shifts. Uncertainty bars are not decoration. They are the honest map of how much those knobs matter. Now to shape and spin. Classic light curve inversion takes time series photometry at multiple viewing geometries and solves for a rotating shape that best reproduces the flicker. With enough well-phased data, the technique reliably recovers the spin period, spin axis orientation, and a coarse, usually convex shape. Convex is not a preference. It is a concession to the mathematics. Given sparse data, allowing deep concavities creates an ocean of solutions that fit equally well. The convex approximation gives you a stable coastline, even if the bays are missing. With dense multi-apparition data, or stellar occultations, you can start carving in topography and non-convex features, but only then. In other words, inversion is powerful, not magical. It thrives on long baselines and diverse phase angles. It sulks when handed 3 nights and 1 geometry. Light curves also carry fingerprints of surface scattering. Not all facets reflect alike. Models like Lamol-Seliger or Hapke describe how roughness, porosity, and grain microphysics tilt brightness with phase angle. Fit the wrong scattering law, and you may mistake surface varnish for shape. That is why observers measure phase curves, brightness versus sun-object-observer angle, to anchor the photometric behavior before dreaming up exotic silhouettes. The opposition surge, a brightening at very small phase angles, is another booby trap. If unmodeled, it can inflate the perceived cross-section and warp inferences about albedo. Activity muddies the water. Dust comets add an almost steady glow that damps rotational modulation. Jets can produce quasi-periodic brightening, unrelated to shape at all. The proper move is to model nucleus plus comet simultaneously, or to choose filters that minimize gas contamination when you are chasing dust, and vice versa. When possible, observers use apertures that grow with geocentric distance, so they always capture the same fraction of a coma. Otherwise, the light curve becomes a barometer for your photometry setup, not for the object. Again, uncertainty bars and method notes are the difference between science and improv. Non-gravitational forces, those tiny pushes and torques, are fit with parametric terms that scale with heliocentric distance. The standard trick assigns a radial component, anti-solar, plus optional transverse and normal components to mimic asymmetric jets. This is useful, but remember the parable of the hammer and the nail. A 3-parameter thrust law can absorb unmodeled astrometric bias, especially when the observing arc is short. If your star catalog has systematic offsets or your timestamps drift by a second, the orbit fit may discover a phantom jet. The cure is independent reductions, updated astrometric catalogs, and a healthy skepticism toward beautiful fits with ugly residual structure. Good practice: compare solutions from different teams and propagate full covariance to prediction times. No cherry-picking the rosiest orbit for tomorrow's pointing. Statistics is not a garnish. Modern teams lean on Markov chain Monte Carlo and nested sampling to explore the many-headed parameter space: spin, shape coefficients, scattering, coma fraction, and non-gravitational terms. The posterior distributions, not a single best number, tell you what the data actually support. Multimodal posteriors, 2 different periods that both work, for instance, are a red flag to slow down and design a discriminating observation. Inverse problems love to hand you equifinality, the situation where many models look great. The job is not to fall in love with the first good fit. It is to break ties with new data. Window functions deserve a shout-out. If you observe every clear night at roughly the same local time, you bake in aliases, false periods that reflect Earth's rotation and scheduling more than the object's spin. The cure is to vary cadence deliberately: short runs, long runs, and multi-longitude campaigns. Amateurs often shine here, filling time zones professionals cannot. A single well-placed data string can slay a seductive alias and rescue a month of work. Spectroscopy brings its own cautions. Weak lines flirt with the noise floor, subtracting sky emission lines is a dark art, and telluric correction can imprint ghosts that masquerade as molecules. Line identifications should survive changes in reduction method, aperture size, and air mass. Report upper limits with the same pride as detections. A good limit is a gate that future theories must pass through, not a shrug. Above all, publish the boring parts: calibration frames, aperture choices, phase corrections, priors, and the rationale for each model component. Models will always talk. It is your job to keep them on script. The best papers read like recipes: ingredients, steps, and the moments you nearly burned the sauce. Next, we'll channel that discipline into a playful scorecard, building a strangeness index that compares physics, chemistry, and geometry without turning nuance into a shouting match. It's the Olympics of weird judges from physics, chemistry, and geometry hold up scorecards. If we want to compare 3 travelers without turning the conversation into a noisy food fight, we need a scoreboard that rewards different kinds of odd, not a courtroom verdict. More like a decathlon, the aim is clarity, not drama. A playful index that still teaches. We will grade 5 events that capture how an interstellar visitor can surprise us. The quiet shove that is not gravity. The neon sign of activity or its absence. The pantry of molecules that hints at birthplace. The direction it chose to enter our sky, and what that says about our surveys, and the flourishes in its motion and spin. Each event runs from 0 to 10, where 0 means ordinary, and 10 means sit up straight. First up is the gentle misbehavior of motion. Call it the mystery push. When an object drifts a little faster outward than gravity alone predicts, we lean in. A subtle, distance-dependent nudge is the kind of plot twist that demands a mechanism. Oumuamua owns this event with a full score. The standard bearer for something else is whispering. 3I Borisov earns only a couple of points here, because while it does show the expected non-gravitational terms of an active comet, nothing about the pattern challenges the textbook. 3IATLAS lands in the middle, a modest nudge that fits a quiet, venting surface and keeps the judges alert rather than astonished. Next is the neon sign factor. Think of a coma as the glowing sign that says open for business. If the object strolls through the warm part of the solar system with a bright halo, no mystery there. If it stays buttoned up, we raise eyebrows. Oumuamua scores high because it kept its sign dark when many cousins would fog up. Borisov scores low because it behaved like a classic coma-forward comet, which is wonderful for science and not especially strange. Atlas sits between them with a faint halo that hints at chemistry without demanding a parade. Chemistry is our third event, the curveball course. Here we listen to the gases that make it to the coma and the dust that rides along. Compositions rich in carbon monoxide at moderate sunlight, or richer in carbon dioxide than expected, earn style points because they point to very cold nurseries or unusual layering. Borisov takes a near-perfect score here for announcing a freezer depth we do not usually see, while Atlas earns a strong mark for a carbon dioxide forward personality that shifts the conversation about where it formed. Oumuamua receives a respectable, inference-heavy number because its crusted, weathered surface kept secrets that we can only approach sideways, which is a kind of mystery even if it is not a laboratory mic drop. The fourth event is geometry versus bias. Interstellar visitors do not file flight plans, but statistics say we should meet more of them from the general headwind direction set by the sun's motion through the local stars. At the same time, our telescopes live in particular hemispheres, so where we discover something can reflect where we look rather than where the galaxy prefers to send it. Oumuamua's approach near the expected headwind earns a solid, not shocking score. Borisov, arriving from a different swath of sky and reminding us that talent does not belong to any one longitude, pushes a bit higher. Atlas, discovered from the south under a Milky Way backdrop, earns an even stronger number because it forced the community to widen its stance and cover the hemisphere that once received fewer patrols. The fifth event is dynamical flare, where the judges reward confident hyperbolas, big turning angles, and rotational drama. Oumuamua's non-principal axis wobble, plus its firm no-return trajectory, score high. Borisov also scores high, not for spin theatrics, but for an orbit so hyperbolic that the sun's bend looks casual. Atlas earns a healthy mark as well. The path is cleanly unbound, and the motion shows all the hallmarks of a traveler who will never send a change of address. Now for the medals. Spoken, not shouted. If you add the feelings behind those numbers, rather than the numbers themselves, Oumuamua remains the champion of puzzle energy. It wins on the quiet shove and the unplugged neon, and its odd rotation is the flourish that seals it. Borisov is the chemistry icon, the one that turns spectrographs into exclamation points while keeping the rest of the performance admirably orthodox. Atlas is the balanced all-rounder, not the loudest in any single event, but strong across categories and invaluable for teaching us how discovery latitude and cadence shape the stories we tell. Why bother with a scoreboard at all? Because it forces us to state our values. If you think chemistry is the strongest teacher, you will weigh that event more heavily and crown a different champion. If you think unexpected accelerations are the ultimate judge of strangeness, you will follow Oumuamua's trail. The rubric makes those choices visible, and once they are visible, they can be argued with evidence rather than intuition. It also makes a promise. Scores can move when new data arrive. A late blooming coma, a measured torque, a refined inbound direction that changes the statistics, any of these could shift the standings without changing the rules. There is a deeper lesson in keeping the exercise playful. Ranking is not the point. Illumination is ordinary behavior in a visitor from another star is itself a result, because it tells us that planetary systems often cook similar recipes and then fling similar leftovers. The true prize is not the gold medal, but the growing archive of how different systems build small bodies, crust them, season them, and send them wandering. The index is a conversation starter, not a verdict. Next, we trade medals for comfort and answer the quiet question that pops up in every inbox. How close do these objects come? What are the real distances? And why interstellar almost always translates to safely far away? Planetary defense loves boring. Interstellar comets are the safest kind of strangers, socially distant by default. Let us start with the headline everyone wants first. These visitors are not on a collision course with Earth. Interstellar objects do not loop, they swoop. Their paths are open arcs that slice through the solar system and keep going, which means they spend most of their brief cameo far from any planet. For 3IATLAS specifically, the closest approach to Earth is projected to be well over 1 astronomical unit, roughly the distance from Earth to the Sun. Its closest pass by the Sun comes near the end of October 2025, inside the orbit of Mars, and then it leaves. That is not a near miss. That is a respectful wave from across the cosmic street. If that is the reassurance, here is the mechanism behind it. When survey teams flag a new object, the first job is to measure its position precisely at multiple times and stitch those positions into an orbit solution. Each measurement narrows the range of possible futures. Think of it like triangulating a friend's location using a handful of texts pinned on a map, except the map is three-dimensional, and your friend is a pebble traveling tens of kilometers each second. As the observing arc grows from hours to days, and then to weeks, the uncertainty cloud around the predicted path shrinks dramatically. For fast hyperbolic visitors, that cloud collapses even faster, because you are not trying to thread a multi-year ellipse past the planets. You are confirming a single pass. Agencies track and score risk in a way that is deliberately dull. Because dull is dependable, discovery coordinates flow to the minor planet center, where they are quality checked and shared with the world. From there, orbit solutions feed into impact monitoring systems, such as JPL's Center for Near-Earth Object Studies and its automated Sentry analyses. Sentry runs an ensemble of slightly different orbits that all fit the data and asks an unglamorous question: do any of those variants brush Earth in the next 100 years or so? If the answer is yes, the system keeps watching. If the answer is no, the object gets a green checkmark and everyone goes back to their coffee. Since interstellar objects are unbound, their ensemble of possible futures diverges away from us. The natural drift of the solutions is outward and onward. The safety workflow includes triage by consequence. For ordinary near-Earth asteroids, 2 scales are common. The Torino scale is the simple color-coded one that translates a risk into a public-friendly number. The Palermo scale is the expert version that compares the calculated risk to the background rate of impacts from similar objects. Interstellar comets rarely get a look in on those scales because their geometry and speed mean they do not enter the corridors where a real risk could be computed. They simply are not on the playing field long enough or close enough. You might wonder why we still invest time tracking them, given the low danger. 2 reasons. First, science. Nailing the path is how we schedule every other observation downstream, from chemistry to spin. Second, stewardship. The same tools that keep interstellar visitors honest are the tools that would alert us to a genuine hazard in the future. Every clean success is a drill that hardens the response. Coordinating telescopes across longitudes, folding in amateur astrometry, updating ephemerides overnight. All of that becomes muscle memory for the system we count on when timing is tight. A common worry is that we could be blindsided by a late discovered object. That is a fair worry for certain classes of near-Earth objects that lurk near the sun in our sky or arrive from awkward angles. Interstellar comets are a different species of trouble. Their inbound speeds are so high and their paths so unbound that if one were ever aimed our way, we would see that intent in days, not months, because the astrometry would immediately fail to fit a safe trajectory. The geometry would scream at us long before the object was close. In practice, what we see for 3IATLAS is the opposite, a steadily improving orbit that stays comfortably far no matter how the math is updated. What about the close approaches to other planets you sometimes see in flyby tables? Those entries are not red flags. They are routine bookkeeping. A passage inside the orbit of Mars does not translate to a bullseye on Mars, any more than flying to a city guarantees you will visit every neighborhood. The distances are still large, and the timing is brief. Gravity will bend the path by a predictable amount, and then the traveler is gone. There is also the visibility wrinkle. Around the time of perihelion, 3IATLAS sits near the sun in our sky from Earth's point of view, which makes observing it tricky for a few weeks. That is an observing inconvenience, not a danger. Once it moves out from conjunction, telescopes pick it up again, log more positions, and tighten the numbers further. If anything, the post-perihelion measurements are a reality check that the earlier predictions were as dull as promised. One last bit of perspective helps. Planetary defense is built to worry about the repeat visitors, objects bound to the sun that cross Earth's orbit again and again over centuries. Those are the ones for which tiny uncertainties can accumulate into real questions, because the same body has many chances to be in the wrong place at the wrong time. Interstellar objects have exactly one chance, and their default behavior is to miss by plenty. In a field that earns its keep by refusing to sugarcoat, this is as sweet as it gets. So breathe, enjoy the science. The galaxy just sent another postcard, and it will not land in your backyard. Next, we gaze ahead. What discoveries the next decade will bring as the biggest new survey turns on, and how often weird space rock might become a monthly headline rather than a once-in-a-while surprise. In the 2030s, weird space rock may be a monthly special. The reason is simple. Discovery power is about to jump from garden hose to fire hydrant. Rubin Observatory's legacy survey of space and time will sweep the southern sky with a giant field of view, returning to the same patches again and again with exquisite depth. That cadence does not just make pretty movies of variable stars. It turbocharges the search for faint movers that used to slip between exposures. A 100-meter interstellar visitor that would have been a rumor in 2017 becomes a scheduled target with weeks of warning. The key word is earlier. Earlier than perihelion. Earlier than the best observing geometry. Earlier than the object fades into the day sky. Earlier buys chemistry, shape, and time to coordinate a small army of telescopes. Finding is half the game. Triage is the other half. LSST's alert stream will push out millions of something changed notifications each night. Most are not interstellar, so machine learning will sit at the velvet rope. Brokers trained on past interlopers will sift for signatures of fast sky motion, non-repeating tracks, and odd brightness behavior that flags a hyperbolic arc rather than a bound wander. Think of it as a giant spam filter with a soft spot for troublemakers. The goal is to recognize a candidate while it is still a whisper, then escalate it before the sky rotates and the chance is gone. With earlier discoveries, follow-up can stop being frantic and start being strategic. On the big mirror end, JWST becomes the chemistry microscope. Mid-infrared spectroscopy at pre-dawn distances lets us catch molecules like carbon dioxide and carbon monoxide before the coma thins to a rumor. JWST's scheduling is tight, but the combination of rapid alerts and target of opportunity protocols means an interstellar visitor with a clear slate could snag windows for decisive spectra. Hubble, meanwhile, remains the size referee in visible light. Its sharp images, plus careful point spread function fitting, can set ruthless upper limits on the nucleus, telling us whether we are chasing a chunky boulder or a sliver with delusions of grandeur. The pairing is powerful. Hubble nails the silhouette, JWST reads the pantry. Down on Earth, a new generation of rapid response spectrographs will keep the assembly line moving. Medium aperture telescopes with high throughput instruments can grab low-resolution spectra within hours, classifying the coma as dust-led or gas-led and flagging unusual blends. Bigger facilities can then step in for detailed line work. Expect more observatories to keep interrupt keys armed, where a single approved trigger turns a sleepy night into a comet stakeout. The ethos shifts from improvisation to protocol. When the bots say hyperbolic inbound, the machines and humans already know their next 12 hours. Not every tool will play, and that matters too. Radar, the hero of close asteroid encounters, will almost always sit this one out. Interstellar visitors are too far and too fast. The signals would be whisper-thin by the time they bounce back. That impossibility clarifies priorities. Pour effort into photometry, spectroscopy, and precision astrometry, not into fantasies of pinging a rock halfway to Mars. Similarly, sample return dreams will remain dreams unless a new class of pre-positioned missions becomes reality. For the next decade, flybys and photons are our instruments. The lab bench will stay on Earth. One quiet revolution will come from smarter coordination. Expect automated schedulers that talk across observatories, handing the target from longitude to longitude like a baton. Expect citizen science portals that present moving object candidates for visual vetting when the algorithm's confidence drops to a shrug, because a trained human can still outwit a glitch. Expect open notebooks, public dashboards that show the orbit fit maturing in real time, the brightness curve growing point by point, and a spectroscopic to-do list updating as clouds and time zones play nice or do not. The community that caught Borisov by enthusiasm will catch its successes by rehearsal. The data themselves will improve in ways that seem small and are not. Better absolute timing means cleaner astrometry at high sky motion. Standardized filter sets and calibration stars stitched into LSST images mean color comparisons that actually compare. Polarimetry will become a routine add-on rather than an exotic garnish, giving us grain clues on nights when full spectra are out of reach. Even twilight observing, historically a nemesis, will be mined more aggressively because interstellar paths do not care about our favorite dark hours. The mantra will be catch it where it lives, even if that means pointing into a glow that used to be a hard no. All of this leads to a demographic payoff. A handful of visitors taught us there is more than one recipe for interstellar small bodies. A dozen per decade would let us ask population questions with a straight face. How often do we see coma-quiet shards versus textbook comets? Do inbound directions cluster around the solar apex once southern coverage is complete? Or was that early pattern an artifact of where our telescopes lived? Are carbon monoxide heavy chemistries rare treats or common staples? Does the distribution of shapes and rotation states hint at formation by gentle aggregation or by violent fragmentation? With numbers, lively hunches become testable statements. There will be plot twists. Some objects will arrive inconveniently close to the sun from our point of view, taunting us while we count down to a safer elongation. Some will parade unusual dust that blindsides our standard models. Some will refuse to show more than a color and a light curve, daring us to infer the rest. But the center of gravity shifts once discovery becomes routine. Instead of debating one odd rock for years, we will slot each newcomer into a growing atlas of behaviors. letting the outliers teach us without letting them dominate the conversation. So yes, prepare for a busier bulletin board. The alerts will ping, the telescopes will swivel, and a few times each year, we will argue over spectra that looked fine until someone corrected the skylines. That is the right kind of noisy. The decade ahead will turn, "Did we get lucky?" into "Who is on duty tonight?" And that is how a field grows up. Next, we close the loop with a verdict that is light on drama and heavy on nuance, weighing which visitor is truly the strangest once physics, chemistry, and geometry have all had their say. Oumuamua is the riddle, Borisov the recipe, and 3IATLAS the new menu item that has the chefs arguing. If strangeness were a single trophy, the ceremony would be short. But weird comes in flavors, and our three guests each bring a different course. Start with the physics category, where motion and behavior either obey the house rules or smirk at them. Oumuamua walks off with that ribbon, a tiny extra shove away from the sun, fading with distance, paired with a stage presence that refused to light a classic cometary glow, is the kind of combination that keeps orbital fitters awake long after the coffee is given up. It is not the magnitude of the nudge that fascinates. It is the consistency. The object behaved like a polite guest, who leaves no fingerprints, and yet somehow moves the furniture. Add a rotation state that reads like a gymnast mid-routine, rather than a calm single-axis spin, and you have a traveler that makes models clear their throats. Physics does not panic, but it definitely raises an eyebrow. Slide over to chemistry, and the spotlight swings hard to Borisov. Where Oumuamua kept its pantry closed, Borisov flung the doors wide open and let the spectrographs feast. Carbon monoxide in headliner amounts at distances where many comets would still be mum. Is not just a fun fact. It is a neon pointer to a birthplace colder than the default picture. The rest of its behavior stayed endearingly, comet normal, which is exactly why the chemistry lands so strongly. Familiar choreography, surprising ingredients. If Oumuamua is a question mark drawn in pencil, Borisov is a bold underline beneath the phrase "deep cold happens." It reminds us that other planetary systems build freezers the way some people build home theaters, enthusiastically and with overkill. Now give the stage to 3IATLAS, the newcomer that insists on caveats and attention. Early notes suggest a carbon dioxide forward personality and a quiet coma, as if the object prefers to speak in a lower register than the classic water-dominated chorus. Its arrival from a southern vantage also nudged the community to widen the net and keep both hemispheres honest. Nothing about Atlas screams headline, yet the way Oumuamua's push or Borisov's overstocked carbon did. But the pattern is already tugging at our priors. It is the dish that arrives at the table and makes the sous chefs argue about spices. A few more nights of clean spectra, or a late change in its dust to gas balance, could promote it from intriguing to agenda setting. Either way, it is the necessary third point that turns a line into a triangle, giving us a sense of the shape of the population rather than just a pair of anecdotes. So who wears the crown? If the contest is pure physics surprise, Oumuamua bows and accepts. Non-gravitational nudges without a loud coma are the plot twist that keeps the fan theories humming and the serious papers cautious. If the contest is chemistry, that forces us to redraw part of the map. Borisov curtsies and reminds us that the galaxy's outer pantries can stock far more carbon monoxide than our parochial experience suggested. If the contest is freshest puzzle, Atlas waves the newcomer's flag, carbon dioxide ahead of water, a demure glow rather than a spotlight, and a sky path that expanded our search habits. The judges are from different departments, and they hold up different scorecards. That is not indecision. It is a cue that strange is multidimensional. The point of a verdict is not to end a conversation, but to tune it. Oumuamua tells us to build better tools for catching faint, fast interlopers early enough to watch the subtle forces act in real time and to check whether radiation pressure or hidden vents are picking pockets. Borisov tells us to expect deep cold chemistry and to refine our ideas about where and how disks can warehouse volatile, rich solids, Atlas tells us not to confuse survey footprint with galactic truth, and to keep an eye on volatiles that wake before water. Each one shifts the center of gravity of our expectations, and together they make a simple moral feel earned. Planetary systems are varied cooks, and the Milky Way shares recipes liberally. There is also a human moral. Our instruments have finally grown into the task, and our networks behave like a team rather than a scatter of soloists. That is why we are here, debating flavors of weirdness with a straight face instead of squinting at a single cloudy image. If the next decade produces a dozen more interstellar visitors, we will stop asking which single rock is the strangest and start asking which families of behavior are common, which are rare, and which scream special circumstances. Strangeness will stop being a headline and start being a histogram. So yes, crown Oumuamua for physics oddity, toast Borisov for chemical bravado, and keep a seat warm for Atlas as the early days harden into a profile. But pin the medals with soft hands. Plot twists in science are peer-reviewed, not foretold, and tomorrow's data can shuffle the podium. A late detection of a faint jet, a refined inbound direction that sharpens a statistical claim, or a surprise surge in an unexpected molecule can tug the crown a few centimeters left or right. That is not a flaw. That is the contract. The universe writes the script. We read it out loud, try to keep the jokes tidy, and update the ending when the next postcard lands.